Hello and welcome to this 17th set of problems on complex numbers. In this set, we will solve problem number 161 to 170. So as I say in all of my videos on maths that when I read the problem, you should try to solve the problem yourself by pausing the video. If you cannot solve the problem yourself, then look at the solution. So without further ado, let's get started. Problem 161 says that if z is any complex number, then show that mod of z by mod z minus 1 is less than equal to mod of argument of z. So for solving this, we let z is equal to r e to the power I theta. So mod z would be r. That is z by mod z is equal to e to the power I theta, that is cos theta plus I sin theta. Now we substitute this value in the given expression, that is left hand side of the given expression, that is mod of z by mod z minus 1 is equal to cos theta minus 1 plus I sin theta. Now this is equal to square root of cos square theta minus 2 cos theta plus 1 plus sin square theta. Sin square theta plus cos square theta is 1. 1 plus 1 2, that is 2 minus 2 cos theta. Now from trigonometry we know that 1 minus cos theta is equal to 2 sin square theta by 2. So 2 minus 2 cos theta is equal to square root of 4 sin square theta by 2, that is 2 sin theta by 2, which will be less than or equal to theta. And that's how we can say that the given expression is less than equal to argument of z, mod of argument of z. Problem 162 says that if z is any complex number, then show that mod of z minus 1 less than equal to mod of z minus 1 plus mod of z into mod of argument z. So we are given that mod of z minus 1. So we can rewrite this as mod of z minus mod z plus mod z minus 1. That is, we add and subtract mod z. So clearly, we know that mod of z1 plus mod of z2 is less than or equal to mod of z1 plus mod of z2. So we can write this to be less than or equal to mod of z minus mod z plus mod of mod z minus 1. Now from the first part of this, we take out mod z common. So it will become mod z into mod of z by mod z minus 1 plus mod of mod z minus 1. So we have just found the value of z by mod z minus 1, that is this part, equal to argument of z. And that's how we have the required result. Problem 163 says that if mod of z plus 1 by z is equal to a, where z is a complex number and a greater than 0, find the greatest and least value of mod z. So we let z is equal to r cos theta plus I sin theta, then 1 by z would be 1 by r cos theta minus I sin theta. So mod of z plus 1 by z will be equal to mod of r plus 1 by r cos theta plus I into r minus 1 by r sin theta. So we square both sides. In this case, this is equal to a, so it will become r plus 1 by r whole square cos square theta plus I into r minus 1 by r whole square sin square theta is equal to a square. So after expanding this, we will have r minus 1 by r whole square is equal to a square minus 4 cos square theta. Now r will be greatest when this r minus 1 by r will be greatest. Spelling is wrong here. That is cos theta is equal to 0. So r minus 1 by r will be equal to a. So r max is a plus square root of a square plus 4 by 2. And for the lowest value, cos theta can be 1 or minus 1. So r minus 1 by r will be equal to a square minus 4. So from this we get r min as a square minus 4 minus square root of a to the power 4 minus 8a square plus 20 by 2. Problem 164 says that if z1 comma z2 be complex numbers and c is a positive number, then prove that mod of z1 plus z2 square is less than 1 plus c into mod of z1 square plus 1 plus 1 by c multiplied with mod of z2 square. So we have this given expression. So what we do is we split the left hand side and we write it in the form of z bar, that is z1 plus z2 multiplied with z1 bar plus z2 bar. And right hand side we have 1 plus c mod of z1 square plus 1 plus 1 by c mod of z2 square. So from left hand side we multiply and we get Z1 square and Z2 square. This should be Z2 square. There's a typing mistake. And then we have two extra terms, Z1 Z2 bar plus Z2 Z1 bar. So we cancel out mod Z1 square and mod Z2 square from right hand side. We will have after that, there is something wrong here. This should be C Z1 square and this should be 1 by C Z2 square. Anyway, so Z1 Z2 bar plus Z2 Z1 bar is less than C Z1 mod Z1 square plus 1 by C mod Z2 square. Now we substitute Z1 is equal to X plus IY1 and Z2 is equal to X2 IY2. So our left hand side is like this, and right hand side becomes 1 by C into C square X1 plus Y1 square plus X2 square plus Y2 square. Now we multiply the left hand side and we find that we will have only two terms, that is 2C X1 X2 plus 2C Y1 Y2. We bring this C to the left hand side, and this is equal to C square X1 square plus C square Y1 square plus X2 square plus Y2 square. Now we bring everything on one side and we will have Cx1 minus X2 whole square plus Cy1 minus Y2 whole square, which is sum of two squares, which will be always greater than 0. And thus we have proven the result. If Z1 and Z2 are two complex numbers such that mod of Z1 minus Z2 by Z1 plus Z2 is equal to 1, prove that I Z1 by Z2 is equal to X, where X is a real number. Find the angle between the lines from origin to the points Z1 plus Z2 and Z1 minus Z2 in terms of X. So we are given that mod of Z1 minus Z2 divided by Z1 plus Z2 is equal to 1. So we can say that mod of Z1 minus Z2 whole square, mod of Z1 minus Z2 square is equal to mod of Z1 plus Z2 square. Now we again write mod Z square is equal to Z bar form. So we have this second line here, and then we cancel out terms. We are left with 2 Z1 Z2 bar is equal to minus 2 Z2 Z1 bar. That is Z1 by Z2 bar is equal to minus Z1 Z2. So you see, this basically means Z1 bar is equal to minus Z. That actually implies Z1 by Z2 is purely imaginary. That means I Z1 by Z2 would be real, which is some real number X. Now we rewrite Z1 plus Z2 by Z1 minus Z2 as Z1 by Z2 plus 1 by Z1 by Z2 minus 1. That is, we divide numerator and denominator both by Z2. Now we write Z1 Z2, Z1 by Z2 as minus Ix from here. So we get minus Ix plus 1 and in the numerator and minus Ix minus 1 in the denominator. Then we multiply with the complex conjugate of denominator to obtain minus 1 plus X square plus 2Ix by 1 plus X square. Once we have found this, we can find the argument tan theta is equal to argument of Z1 plus Z2 by Z1 minus Z2, which will be equal to 2x by x square minus 1. Problem 166 says that let Z1 comma Z2 be two complex numbers and A be two real numbers such that A square plus B square is not equal to 0. Prove that mod Z1 square plus mod Z2 square minus mod of Z1 square plus Z2 square is less than equal to 2 mod of A Z1 plus B Z2 square divided by A square plus B square is less than equal to mod of Z1 square plus mod of Z2 square plus mod of Z1 square plus Z2 square. So here we take Z1 as R1 cos theta 1 and Z2 is equal to R2 cos theta 2 plus I sin theta 2. And we also let A is equal to R cos alpha and B is equal to R sin alpha. So we first compute A Z1 plus B Z2 square, that is mod of A Z1 plus B Z2 square. So it is a matter of trigonometrical and algebraic manipulation, and we arrive at the end result as R square by 2 multiplied with R1 square into 1 plus cos 2 alpha plus R2 square 1 minus cos 2 alpha plus 2R1 R2 sin 2 alpha cos theta 1 minus theta 2. Now this 2 mod of A Z1 plus B Z2 square divided by A square plus B square, this should be plus, is equal to R1 square plus R2 square plus R1 square minus R2 square cos 2 alpha plus 2R1 R2 cos theta 1 minus theta 2 sin 2 alpha. Because A square plus B square will be R square, so R square will cancel this R square and this 2 will cancel this 2. Now we rewrite this as A plus B cos 2 alpha plus C sin 2 alpha. So A would be R1 square plus R2 square, B would be R1 square minus R2 square, and C would be 2R1 R2 cos theta 1 minus theta 2. Now we observe that minus square root of B square plus C square is less than equal to B cos alpha plus C sin alpha less than equal to square root of B square plus C square. We add A to everything. So this is true, and so this becomes a minus square root of b square plus c square less than or equal to 2 mod of a z1 plus b z2 square divided by a square plus b square, which would be equal to less than this, which will be less than or equal to this. Now b square plus c square would be r1 to the power 4 plus r2 to the power 4 minus 2 r1 square r2 square plus 4 r1 square r2 square cos square theta 1 minus theta 2. Now mod of z1 minus z2 square, mod of z1 square plus z2 square we compute, we get this equal to b square plus c square after algebraic and trigonometric manipulations. So a is equal to mod of z1 square plus mod of z2 square, and thus we have proven the desired result. Problem 167 says that if b plus ic is equal to 1 plus az and a square plus b square plus c square is equal to 1, prove that a plus ib by 1 plus c is equal to 1 plus iz by 1 minus iz, where a, b, c are real numbers and z is a complex number. So we are given that z is equal to b plus ic by 1 plus a. So we compute iz, which will be equal to minus c plus ib by 1 plus I, and then we take the reciprocal of this 1 by iz is equal to 1 plus a by minus c plus ib. Now we perform componendo and dividendo on this, we get 1 plus iz by 1 minus iz is equal to 1 plus a minus c plus ib divided by 1 plus a plus c minus ib. Now we are also given that a square plus b square plus c square is equal to 1, so a square plus b square is equal to 1 minus c square, that is a plus ib into a minus ib is equal to 1 plus c into 1 minus c. So we rewrite this as a plus ib by 1 minus c is equal to 1 plus c by a minus ib is equal to 1 by u. We have assumed this fraction equal to be 1 by u. So now it's a matter of substituting in 1 plus iz by 1 minus iz and finding out that this is equal to a plus ib by 1 plus c. Problem 168 says that if a, b, c up to k are all n real roots of the equation x to the power n plus p1 x to the power n minus 1 plus p2 x to the power n minus 2 up to pn minus 1x plus pn is equal to 0, where this omega is extra, this shouldn't be there, where p1, p2 through pn are real, show that 1 plus a square into 1 plus b square up to 1 plus k square is equal to 1 minus p2 plus p4 minus so on whole square plus p1 minus p3 plus so on whole square. So since a to k are roots, we can write that as x minus a into x minus b up to x minus k is equal to given polynomial expression. Now we substitute x is equal to I, we get this. That is, instead of x, we write I everywhere. Now we divide by in, I to the power n, left hand side becomes 1 plus ia into 1 plus ib up to 1 plus ik, and right hand side becomes 1 plus p1 by I plus p2 by I square, and so on. So p1 by I can be written as minus p1i, and p2 by I square can be written as minus p2. So we take modulus and square, g is missing here in squaring, we get the desired result. Problem 169 says that if fx is equal to x to the power 4 minus x cube plus 4x square plus 4x plus 39 and f3 plus 2y is equal to a plus ib, find a is to b. So 3 plus 2i is one of the values, that is, it is one of the roots of the equation. So when x is equal to 3 plus 2i, that is x square minus 6x plus 13 is equal to 0, we compute the fx. So fx becomes x square minus 16x plus 13 into x square minus 2x minus 21 minus 96x plus 312. Now in this we substitute x is equal to 3 plus 2i. So this whole term would become 0 and 96 would be multiplied with 3 plus 2i, and then 312 is there. So this gives us 24 minus 192, which is equal to a plus ib. You compare real and imaginary parts, a is equal to 24, b is equal to minus 192. So a is to b is equal to 1 is to 8. Problem 170 says that let a and b be two complex numbers such that a by b plus b by a is equal to 1. Prove that the triangle formed by origin and these 2 points is equilateral. We are given that a by b plus b by a is equal to 1, that is a square minus ab plus b square is equal to 0. So a is equal to b plus minus square root of 3ib by 2, that is minus omega square b. Similarly, if you try to find b, it would be minus omega a minus omega square a. So mod of a is equal to mod of b. Now mod of a minus b would be minus omega b minus b, or mod of minus omega square b minus b. So the first one becomes omega square b and the second one becomes omega b. So we can say that mod of a minus b is equal to mod of b. So all three magnitudes are equal. That's why the triangle is equilateral. With this, we come to the end of 17th set of problems on complex number. If you have a comment or suggestion, or you want to say something, please make use of the comment box and let me know about what you think. If you found this video useful and informative, please subscribe to the channel and like the video. Do not forget to press the bell icon so that you can receive notifications when new videos come. And by sharing and liking, you can help fellow students like yourself to reach this video. I'll see you in the next video. Thanks a lot for watching. Enjoy.